So I'll talk about, my title is called Chiral Anomalies in CPT. The talk will consist of two parts. I think maybe some of the people in the audience has heard the first part, but we have some new results in the second part regarding CPT. This talk will be based on this series of work, mostly based on the first paper with Arko Chatterjee, who was a student at MIT and has graduated last year. Now is a postdoc at Stony Brook. And also with Shao, who is currently an MIT student who is moving to IAS as a postdoc. The second half of the talk will be based on some work in progress with another student, Elijah, with Shao and Elijah are both in the audience. It will also be related to a paper I wrote with Nati and Wu Chen last summer. All right, so let's get right into it. So in recent years, we have seen a lot of development in our understanding of symmetries in continuum quantum field theory and in lattice system. A very natural question to ask is, can we leverage this new development to get new insight on a very, very old questions in theoretical physics? Namely, how do we realize chiral symmetries on the lattice? Now, obviously, one motivation for this question is that our universe, the standard model, is chiral. And you would like to realize either chiral global symmetry on the lattice or even construct chiral gauge theory on the lattice. So let me say it more explicitly. The question we would like to address is that given a continuum quantum field theory, that's going to be our target. The quantum field theory in the rest of the talk will be non-chiral by itself, but that quantum field theory will have some chiral global symmetries, and possibly with some anomalies. And we ask ourselves, can we find the lattice discretization of the quantum field theory that also realize its chiral global symmetries? Now, to approach this question, probably the simplest possible setup you can imagine is to consider the 1 plus 1D free massless Dirac fermion. It's the lowest dimension possible, and to have continuous chiral symmetry, this is the minimum theory to consider. So a Dirac fermion in 1 plus 1D has two components, psi left and psi right. Both of them are complex. The Lagrangian takes this form. The left-moving Weyl fermion psi left doesn't talk to the right-moving fermion psi right. There are two obvious U1 symmetries. The first one rotates both the left mover and the right movers by the same phase. Let's call it the vector symmetry. And the second one, let's call it the axial symmetry that rotates the left-moving fermion and the right-moving fermion by the opposite phase. And since the left mover and the right movers don't talk to each other, these two U1s are both exact symmetries, and since they are just rotating by phases, the entire group is a direct product between the two. The U1 vector rotation commutes with the U1 axial rotation. They share the same pi rotation. If you take theta to be pi, for the two U1, both of them flip the two fermions by a sign. So you have to keep track of a global quotient, but that's not going to be terribly important for the rest of the talk. But it's good practice to keep track of the global form of the group. All right, so this is our target. Let's see how to realize this model on the lattice. Yeah? Excellent question. Yeah, excellent question. So in the continuum, it's much more natural to write the symmetry group as U1 left times U1 right. But for reasons that will become clear in the next slide, I will work with this vector and axial basis. The two bases are differed by the vector charges, the sum of the left and the right. The axial charge is the difference between the left and the right. And that relation is the reason why there's a Z2 quotient. All right. All right, so how do we put this system on the lattice? We're going to work with Hamiltonian lattice system. Time is continuous, space is discrete. Now, very naively, since in the continuum we have two complex fermions per space-time point, psi left and psi right, naively you would like to put two complex fermions per lattice site, which I label by J. But there's a famous issue with that, which is known as the fermion doubling problem. In the continuum, the dispersion relation is linear. The energy is linearly proportional to the momentum. But on the lattice, any dispersion relation has to be periodic in the Brillouin zone. So for instance, if the dispersion relation is a sine function, you will have two intersections with the zeros. Near one intersection, that will give you some right-moving fermion. In the other intersection, that will give you some left-moving fermion. So the upshot is that on the lattice, you buy one and get one free. The left and the right fermions always come in pairs. So if you naively put two complex fermion operator per lattice site, you will end up with two Dirac fermion fields in the continuum limit, which is twice as much as you were hoping for in the first place. So how do we fix this doubling problem? Well, you get a factor of 2. To cancel that, you want to multiply it by 1/2. So instead of having two complex fermion per site, why don't we just have one complex fermion at every lattice site, which I denote by Cj. The Cj's obey the standard anti-commutation relation for the fermion operator. And so this is the Hilbert space. For finite L, this is the 2 to the L dimensional Hilbert space. And the Hamiltonian we're going to start with is just the tie-binding Hamiltonian. In high-energy physics, this is known as the stagger fermion Hamiltonian. So just nearest neighbor interaction, C dagger C, so that we preserve a U1 symmetry. This Hamiltonian you can check goes to a single non-chiral massless Dirac fermion in the thermodynamic limit. So in a way, we are halfway done. We find the lattice model that goes to the desired quantum field theory we want. The rest of the talk will be about how to realize the global symmetries of the continuum theory exactly on the lattice. Yeah.
Does it have the exact symmetry that you can scatter from a right movement to a left movement?
You say it doesn't or does?
Maybe at low energy, your effective theory does, but the lattice doesn't.
Yeah, so that's what I thought before I work on this project. Yeah, so I'll get to the punchline in 2 slides. Yeah. So there's one manifest U1, that's the easy one, that just rotates the fermion by an overall constant phase. We can call that the vector symmetry. And the question is exactly, Matthew, what you just asked, where's the other one? Now, there doesn't have to be the other one. The other one could be just emergent, and it doesn't have to be there on the lattice. But is that really the case for this tie-binding Hamiltonian? There's also a conceptual reason why people typically believe that the second U1, the axial U1, isn't there on the lattice. And that's because in the continuum, the vector and the axial symmetry have an anomaly. This anomaly was first discussed by Schringer in the late 50s. But in my opinion, if you really look into that paper, Schringer got all the equations right. But the right physics, in my opinion, was really spelled out in this paper by Ken Johnson in '63. Anyway, the statement is the following. You take the free Dirac fermion. It has the vector and the axial symmetry as their exact global symmetries. The statement of the anomaly, which goes by the name of Schringer anomaly, is that the axial global symmetry is broken the moment you gauge the vector global symmetry. In equations, it says that the Noether current for the axial symmetry is no longer conserved the moment you activate the electric field for the vector symmetry. This is a perturbative anomaly captured by the one-loop Feynman diagram listed over there. This is like a baby version for the more famous ABJ anomaly. In fact, this paper was written in '63, and if you look at the paper by Bell and Jakif, they did acknowledge Johnson's paper for inspiration of their discovery. Now, perturbative anomalies captured by Feynman diagrams are particularly challenging to realize on the lattice, especially with fine-dimensional local Hilbert space. That's the setup we are working with today in this talk. Namely, on every site, we just have some two-dimensional Hilbert space. And there are rigorous theorems in higher dimensions, such as the one by Fikowsky and Chen-Ke-Shu, proving that under various assumptions, such perturbative anomalies cannot be realized on such simple Hilbert spaces. Having said that, if you are willing to work with infinite-dimensional local Hilbert spaces, such as model known as the modified Villen model, then perturbative anomalies can be realized on these more convoluted setups. I'm listing some recent references on this direction. But today, I'm going to stick with fine-dimensional local Hilbert spaces. All right, so that's the background. And now let me give away the punchline of the talk. So this is the Hamiltonian we start with. This is not going to be the only Hamiltonian we consider, but this is a starting point. And contrary to what Matthew was expecting, I'm going to claim that we will realize both the vector and the axial charges exactly on the lattice. And what do I mean by that? I mean, I'm going to write down for finite L, for finite system, lattice system side, I'm going to write down a conserved operator QV and a conserved operator QA. Both of them commutes with the Hamiltonian exactly. Both operators have integer eigenvalues. So the moment you exponentiate it to get a unitary operator, e to the I theta q, that's going to generate the honest-to-God compact U1 global symmetry. The group is U1, it's not Z, it's not R, it's not Q mod Z, it's the vanilla U1. It has many more properties, which I'll discuss down the road, but these are the two most important ones. But there's always a but in theoretical physics. On the finite lattice, the only catch is that the vector charge and the axial charge do not commute with each other. But as you take the continuum limits, the commutator becomes a zero operator. So it's a rather novel way how the axial symmetry is realized exactly on the lattice. This is going to be the first half of the talk. In the second half of the talk, I will say in what sense this lattice chiral symmetry generated by QV and QA have an anomaly, and how that anomaly will be matched with the continuum Schringer anomaly, especially the moment you also impose a lattice CPT symmetry. All right. So that's the punchline. And then after this slide, I'm going to get into the details. So usually, I've given this talk a couple of times. So usually, in the next slide, I'll give the derivation for the axial charge. But after a few trials, I noticed that this is usually the point where people fall asleep. So instead of giving you the derivation, which takes me like maybe 2 or 3 slides, it's a very physical, simple derivation, but I'm not going to do that today. I think people just don't like derivation if the answers make sense. So instead of giving the derivation, I'm going to present you the answer in what I personally find an amusing way. And throughout the entire projects, we just have one trick. We really just have one trick, and the trick is to be real. So I don't really know about you guys, but when I first learned numbers, I started by learning real numbers, and then I move on to complex numbers. But if you think about fermions, it was exactly the opposite, right? We first learned Dirac fermion, and then we learned Majorana fermions. Of course, there's a very good reason behind, and everybody in the audience knows. But for the purpose of this talk, it was absolutely crucial that we think about the complex fermions in terms of real Majorana fermions. So the first thing we are going to do is that we're going to take the complex fermion operator Cj per site and decompose it into 2 real Majorana fermions, which I denote by A and B. So C is Aj plus Ibj, and Aj and Bj are real fermions obeying the self-adjoint property. This is their anti-commutation relation. If you take the tie-binding Hamiltonian, it just decouples into 2 gapless Kitaev chains. So as promised, I'm just going to write you the answer now. Well, before I get into the axial charge, let's start with the easy one. Let's start with the vector charge. The vector charge, which just rotates every complex fermion in an on-site manner by an overall constant phase, takes the form, when written in terms of the real Majorana fermions, takes this form. Now, I'm going to write this formula in a graphical way that will turn out to be somewhat illuminating. So in this picture, I'm drawing these 2 dots close to each other compared to this other 2. And the reason is that you should think about this red circle as a physical site labeled by j equals to 1. But I'm splitting that physical site into 2 Majorana fermions, A1 and B1. And the fact that I'm circling them means that in the expression for QV, A1 is multiplied by B1, and in the next circle, A2 is multiplied by B2. Okay, just some simple graphical way to present the operator on this lattice. Now, if you are someone who has attended at least 1 meetings of UQM in the past 7 years, your brain must be programmed in such a way, like ChatGPT, to predict what the next figure will be. And indeed, not surprisingly, the next figure of the slide will be the Kitaev chain. And in the current context, that corresponds to another operator acting on this Hilbert space. And the main claim of the talk is that that operator is the axial symmetry on the lattice. So it's here, this operator couples A1 with B2, A2 with B3, so on and so on. All right, so that's the answer. And I'm going to, in the next slide, so before I move on to the next slide, I have to confess, I don't really understand this graphical presentation or what the conceptual meaning behind. It's a very curious equality because we are expressing the charge or the symmetry of a Hamiltonian in terms of the Hamiltonian for different topological phase. And I feel like I'm still grasping the potential deeper meaning behind this. Nonetheless, let's take this definition and see what's good about this operator QA. All right. I know many people insist with working with the complex fermion, so you can also write it in terms of C. And what are the properties? It's easy to show that QA, this operator, exactly commutes with the tie-binding Hamiltonian we start with. So in that sense, this is a conserved quantity. Second, this operator you can also easily show has integer eigenvalues, so it is quantized. Therefore, e to the I theta QA is a unitary operator that generates a compact U1 global symmetry. Third, as you might already notice, this axial symmetry is not an on-site symmetry, but it is locality preserving. In what sense? It means that if I start with a finite range local operator, say the operator, the fermion operator located at site J, after the axial symmetry rotation with any value of theta, the output is also a finite range operator. For on-site symmetry, the output will be strictly at the same site. But for my exact axial symmetry on the lattice, it gives some linear combination of the operator on the right-hand side. The details don't really matter. The only thing that matters is that the right-hand side, even though it's not on site, it only involves operator that are nearest neighbor next to the site J. So it's a locality preserving compact U1 global symmetry. It's almost as good as you can possibly hope for. But then as alluded already in the introduction, the only catch is that it doesn't commute with the axial vector charge. And that is obvious because from this, from this expression. In this expression, we map an operator Cj to some combination that also involves C dagger. That's why the two U1s don't commute. Yes.
Just a quick question. So if I think of, say, I generate linear combinations for the right and left charges based on this axial and vector charge, is the action on Cj strictly giving Cj plus 1 for the right and Cj minus 1 for the left? Or
so yeah, so you see, there's a reason I stick to vector and axial. How do you get the left moving charge? Right? In the continuum, you will be taking the sum or the difference of the vector and the axial. But the fact that they don't commute means that you cannot simultaneously diagonalize them. So even though they separately have integer eigenvalues, their sum and difference will not have integer eigenvalues and will not generate a compact U1 global symmetry. That's actually consistent with the anomaly structure in the continuum. In the continuum, the vector U1 symmetry has no anomaly. The axial U1 symmetry also has no anomaly in the continuum. This is to be contrasted with the 3+1D physics, where the axial symmetry does have a self-anomaly. So there's really nothing funky about the U1 axial symmetry because it doesn't have any anomaly. It's just that the vector symmetry and the axial symmetry, they don't see eye to eye with each other. And on the lattice, that is manifested by the fact that they form a non-abelian algebra. Their commutator, as a sanity check, indeed vanishes in the continuum, as you can check. Oh, yes?
Is this non-commutativity the same as the Shu-Heng anomaly?
That's an excellent question. And the short answer is that I don't really know. Yeah, I don't really know in what sense we can view the non-abelianness of this algebra on the lattice as a manifestation of the Schrödinger anomaly in the IR. But later on, I will talk more about, is there a sense of anomaly on the lattice? So hold on to that thought.
Two quick questions. Just you walked us through the commutation of QA, but same thing holds with QB.
Absolutely.
Right, right.
Yeah, QB is the easy one.
Yeah, yeah. And so now for this commutator, is this commutator the same, it's non-zero and it's the same for open and periodic boundary conditions, or is that?
So here we always work on the closed chain.
So it's actually a bulk operator. You haven't written what the commutator is.
That will be on the next slide. So I have nothing against with the lattice. Well, first of all, the lattice translation will give you a discrete symmetry in the IR at half filling. At generic filling, that will give you something more interesting. And I have nothing against that. I just want to point out that this QA will give you a compact U1 symmetry on the lattice, whereas the lattice translation will give you something else.
Do you mind how you take the continuum limit? I always thought you just looked on length scale.
Right, so by continuum limit, or what do I mean that the commutator vanishes in the continuum limit? Yeah, so, so we said that more carefully in the paper, but let me say it in words. So we first take some finite L, and we look at some low-lying state, maybe the first 20 states as you diagonalize the Hamiltonian. What we can show is that take any two of those first 20 states, consider the matrix element of the commutator, and then send L to infinity. That matrix element will vanish for any finite low-lying state. So in that sense, I say the commutator vanishes in the continuum limit. It has zero matrix element on the low-lying state. Yeah, Brandon.
They generate? Like, do they participate in a finite
It
dimensional?
is not only sensible, it's my next slide. Yeah. Ah, 1 over L. 1 over L. So there are already two questions asking what that algebra is. So every time you have two conserved quantities, you take the commutator and you find that it's non-zero, you should be happy. You shouldn't be sad. That means you get the third conserved quantity. If someone hand me poly X and poly Y, I take the commutator, I got poly Z. Great, I got the SU2. But here, what do I get? It turns out that the algebra I got is much more complicated than SU2. To describe that algebra, I have to define many more operators. So define Qn in a similar way I define Qa, but now I'm shifting the A and the B fermions by n sites apart. And n is going to run from 1, 2, 3 all the way to the entire lattice system size. And I also define some other operator Gn, that's some fermion bilinears. Qv is the first one, Q0. Qa is the second one, Q1. And the claim is that if you start with Qv and Qa, you take the commutator, the smallest algebra, the smallest closed algebra they form will involve all the Qn's and Gn's. Okay? And this algebra takes this form. All right, don't worry too much about the details. The two Q's don't commute. G is the thing that will go to 0 in the continuum limit. So Arco and Shao and I, we work out this algebra. We have the independent derivation for Qa, we work out the algebra, and we stare at it. And then we ask ourselves, has anyone, any physicist at all in the history of physics ever written down this algebra? Now, much to our surprise, this algebra was first written down by Lars Onsager in his original 2D Ising model paper in 1944. And this algebra was henceforth known as the Onsager algebra. And what we are finding here is that at the UV level, there's an exact Onsager algebra symmetry for this tie-binding model. And that flows in the continuum limits to the U1 vector and axial symmetry. I would also like to point out this paper by Paul Fendley, where they discuss this Onsager symmetry in a closely related spin chain system. Okay. So we have many more conserved quantities. And in fact, as you take the continuum, you start with QV and QA, which I emphasize are locality preserving. But the funny thing about this entire algebra is that as you take more and more commutators, the resulting conserved charges become more and more non-local. So even though you start with something completely innocent, because they don't see eye to eye with each other, you generate something ultimately non-local. If you fix the n and take the continuum limit, you find that Qn becomes the vector charge for even n, and Qn becomes the axial charge for odd n. So in the continuum, you don't get that many more symmetries. You just get the vector and the axial symmetry. Yes. For that particular Hamiltonian, they are all exact conserved quantities on the lattice. Not necessarily. So I will discuss what are the possible deformations that will preserve these symmetries. So the upshot is that the abelian U1 vector times U1A chiral symmetry in the continuum can arise from this rather bizarre non-abelian Onsager algebra on the lattice. So let me summarize. We realize an axial charge that generates that has quantized eigenvalue. Its only catch is that it doesn't commute with the vector charge, but it generates a compact U1 global symmetry. Now you might think, if we try a little bit harder, maybe we'll be able to find another axial charge operator on the lattice, which has the same continuum limit going to the same axial symmetry in the continuum, but it commutes with the vector symmetry. And that's what we did. So if you try a little bit harder, you'll find a different axial charge, which I call Q tilde A. It's a different lattice operators, but it has the same continuum limit as QA. And it commutes with the vector symmetry. But now the catch is that it doesn't have quantized eigenvalues. Now you might again think, Arco, Shao, Shu-Heng, we're just a bunch of amateurs. And if someone more serious try even harder, then that person will find the axial symmetry on the lattice that both commutes with the vector charge and has integer eigenvalues. I should say that for the Q tilde A, because it doesn't have quantized eigenvalues, it would ultimately generate the R global symmetry. But it turns out that it's not because we didn't try hard enough, but there just cannot be a lattice operators that obey one, that is quantized, and two, commutes with the vector charge. Because if you have such an axial charge, then you can take the sum and the difference with the vector charge and get a quantized conserved left-moving charge. And the presence of that purely left-moving lattice operator would have violated the famous Nielsen-Ninomiya theorem. Also, the more recent generalization of that theorem by Nikita and Anton. So this is the best you can do. You have to sacrifice at least one of the two conditions, and these are the options. Okay. Now that we have realized some exactly conserved operators on the lattice that flows to the continuum chiral symmetry, the natural next question is that, is there an anomaly on the lattice? And if so, in what sense? Now, this gets a little bit tricky because traditionally we define the anomaly, or more precisely, the 't Hooft anomaly of a global symmetry as the obstruction to gauging that global symmetry. But in our context, let's focus on the quantized axial charge. Even though QV and QA are perfectly locality preserving, their nested commutator will ultimately give you something non-local. So it's not entirely clear that if there should be a notion of gauging such non-local charges. Nonetheless, we can prove the following. We can show, so we start with the tie-binding Hamiltonian, but then you can ask, what are the other Hamiltonians that commute with our lattice chiral symmetry? We show that any finite range Hamiltonians, namely local Hamiltonians, that commutes with QV and QA is necessarily gapless. So it's a very strong constraint, and it has the same consequence as the 't Hooft anomaly of a continuous chiral global symmetry in the continuum. I should emphasize that such constraint from the lattice operator QV and QA is even stronger than the typical LSM type constraint. The typical LSM type constraint tells you that the low energy phase cannot be trivially gap. But the allowed options are it could be gapless or it could be symmetry breaking. But here we are talking about some continuous global symmetry on the lattice. In 1+1D, and we proved in 1+1D when it's spontaneously broken, we typically expect ghost on boson mode. But what we can concretely show is that they in fact enforce gaplessness. We can call this a very strong form of symmetry enforced gaplessness on the lattice. Now, what should be called a 't Hooft anomaly has been an active topic of debate, I think, in this collaboration and in also many other collaborations. So just to assure you that I'm not using that word in a controversial way, let's take a look at what 't Hooft called an anomaly in his original 1980s paper. So in his original 1980s paper, in the abstract, he said chiral symmetry must then be responsible for the masslessness of these fermions. So I hope the theorem we are proving here justifies the use of lattice anomaly in this context. All right. Okay, so that's the first part of my talk. Now I'm going to, yeah, Cynthia.
So, just to understand the statement in the Hooft solution statement, was it justified in making that statement that the anomaly identified precludes the gap phase?
Yeah, that's what he argued. What do you mean justify? Sorry, say again.
Given the modern understanding,
Yes.
can the anomaly that he identified be saturated by a gap phase or not?
No. No, because the anomaly that 't Hooft considered in his paper are some perturbative anomalies in 3+1D. They show up in the operator product expansion coefficients of local operator, and those can never be saturated by any gap phase. Yeah, and here I'm talking about the 1+1D version of that. And this, the Schringer anomaly, the 1+1D analog of that, also show up in the operator product expansion of local operator. In fact, it's easier because in this context, it shows up in the 2-point function of the Noether current operator. And that can never be captured by a gap phase. So what we prove here on the lattice actually matches perfectly with our continuum expectation. Okay. All right, so we have argued that the lattice chiral symmetry we found is anomalous in the sense that it enforces gaplessness. But anomaly shouldn't be a binary question. It shouldn't be just yes or no. You know, we're serious physicists, so we would like to get some numbers out of it. Is there some kind of index that we can compute? So that brings us to the notion of the order of the anomaly. So let me define that on general ground. And the order of the anomaly will be a quantity that captures how anomalous this symmetry is. So the definition is very simple. So given a quantum system T, could be a quantum field theory, could be a lattice model with some global symmetry G. The order of the anomaly for G is defined as follows. So you take n copies of the system, n layers of them. Each layer has a global symmetry G. So n layers of them will have G to the n symmetry. But I'm going to focus on the diagonal G symmetry that acts in a uniform way on every layer. The order of the anomaly is defined as the smallest integer n, such that the diagonal G symmetry in this n-layer system is anomaly-free. And for those of you who are familiar with SPT phases and invertible phases, this is indeed related to the way how we define the order of an SPT phase. Okay, with this definition in mind, we can ask, what's the order of the anomaly for our lattice chiral symmetry? Yeah.
In the continuum case, it's infinite order?
Yes. But let's start with the lattice. So the order of the UV anomaly for our Onsager algebra turns out to be 2. Okay, how do you see that? Let's take 2 copies of our system. So now on every site, you will have 2 complex fermions, so 4 Majorana's. So I'm labeled the 2 layers by up arrow and down arrow. For 2 layers of the system, consider this Hamiltonian. It's an interlayer coupling, which is graphically presented over there. This Hamiltonian respects the diagonal Onsager symmetry. So this is a Hamiltonian that's invariant under the diagonal Onsager symmetry, and you can easily show that this Hamiltonian is trivially gap. So it's completely featureless. So that means as you take two copies of our fermion system, the anomaly for the lattice chiral symmetry cancel with each other. And that shows that the order of the anomaly on the lattice is only 2. And as Dan was already anticipating, on the other hand, the order of the IR shrinker anomaly for U1b times U1a is infinite. And the reason is, again, my answer to Senthil's question, that this is, in the IR, this is an anomaly captured by the operator product expansion coefficient. Those coefficients are real numbers. So no matter how many copies you take, the real numbers are still there. So it's an infinite order torsion-free anomaly. And this, as I say, is common for perturbative anomalies captured by Feynman diagram. So you may say that there's a slight mismatch between the order of the anomaly in the UV and the IR. And in a sense, the IR symmetry is more anomalous than its UV counterpart. That's not a contradiction, because anomalies can be emergent every day. And furthermore, the IR QFT has more symmetries. Among other things, the IR QFT has a continuous Lorentz group symmetry. So it's natural to wonder, maybe if we impose more symmetries on the lattice, the orders of the anomaly will match between the UV and the IR. No, we don't have to impose those symmetries, but if you want to get a better match with the continuum, it's a natural question to ask. But obviously, it's too much to impose a continuous Lorentz group symmetry on the lattice. On the lattice, we're working with a Hamiltonian lattice system. The time and space are treated in very different ways. So if only there were a natural symmetry present in every quantum field theory that could be further imposed on the lattice, then we can make a more interesting comparison. And that brings us to the CPT symmetry. The CPT theorem, proven in the late 50s, is that every local unitary Lorentz invariant quantum field theory has an anti-unitary symmetry that simultaneously reflects one spatial coordinate and the time coordinate. Historically, this symmetry is known as the CPT symmetry, but it's really a terrible name. It's more appropriate to call it the CRT symmetry because in general dimension, especially in our space-time dimension, it's really the reflection that's involved in the action. But in this talk, we're going to be in 1 plus 1D, so there's no difference between parity and reflection. Yeah, next. Yeah, but I thought it was, in the beginning, it was proven by assuming Lorentz symmetry. Maybe I was wrong. Am I wrong?
Certainly the gaplessness, the initial proof, assumes Lorentz symmetry, and you look at some correlation functions of currents, right? And you argue that there has to be a pole. But I thought now from kind of our modern understanding that, like if you think of this system as living on the edge of some, I don't know, quantum Hall type system, right? Then you know that the bulk is topological, so there is always an anomaly.
But the original CPT theorem, I think, was proven by assuming the Lorentz symmetry.
I'm not talking
about sorry.
I'm talking about one slide before that.
Sorry.
You were saying that to match, we have to impose this Lorentz symmetry or something like Lorentz symmetry.
Yeah. Oh, yeah. So indeed, I'm not going to impose Lorentz symmetry. I'm only going to impose CPT.
But then I'm just saying that in the continuum, right, Lorentz symmetry is not crucial for the anomaly, right?
No, I agree with that, yeah. So I'm not going to impose it on the lattice. Yeah. And I don't even know a way to impose that on the lattice. So I'm only going to impose the CPT. Any other questions? And I would like to argue that CPT in the continuum is really more fundamental and universal than the separate reflection symmetry and the time reversal symmetry. There are many quantum field theories that have no reflection, no parity, no time reversal, but there's a CPT symmetry. And my favorite example is the standout model, which I would say is a physical example. So if you are looking for a natural symmetry to impose on the lattice, maybe CPT is a natural option. So that brings us to the lattice CPT. So in this paper I wrote with Nati and Wu Chen last summer, we considered the following CPT symmetry on this Hilbert space of fermions. So it takes Cj to C dagger minus j plus 1. And it's an anti-unitary operator, so it also maps I to minus I. But on top of that, it does a reflections around the link 0, 1. And in that paper, we analyzed various examples and argued that this is the correct lattice transformation or operator that flows to the continuum CPT. So in this ongoing work with Elijah and Shao, we show that the order of the chiral anomaly on the lattice it becomes infinite the moment we impose CPT on top of the Onsager symmetry. And that matches with the continuum. In particular, the earlier interlayer coupling that drives the two-layer system to a trivial phase is now forbidden by the CPT. So let me just summarize what we have talked about so far. So in the UV, we start with this Hamiltonian that flows to that continuum Lagrangian. The IR has two U1 symmetries that commute with each other. In the UV, we have a vector symmetry that's the obvious one. And the punchline of the first part of the talk is that there's a second exact symmetry, U1A, that acts on the fermions in a more complicated way. But the order of the anomalies don't match. But the moment you impose a lattice CPT on top of all this, then they match. There's a similar story if you only consider half of the system. Yeah, Brendan. It turns out that if you impose Onsager in CPT, you can literally write down all the possible deformation that respect the symmetries. It's an infinite dimensional space, but you can prove that it's always gapless. Yeah, it turns out to be quadratic. Yeah.
And the ones that can compute just with Onsager is also.
That's right. So the CPT eliminates some other quadratic terms, such as this interlayered term. Yeah.
I answered that before, but I don't remember the answer.
Yeah.
If you go to momentum space,
You don't even have to finish, but I'll let you finish.
I'm sure you'll say it better.
Okay, so Nati's question. So Nati's question was, if you start with a tie binding model, go to momentum space. Then at each point in momentum space, there's an independent there's a rotation you can do independently at each point in momentum space. So the free fermion tie binding Hamiltonian has an enormously large symmetry. That's you can say is local in momentum space. Now, is our Onsager symmetry part of that? The answer is no. Our Onsager symmetry does not belong to that very large abelian symmetries generated by going to the momentum space. The easiest way to see that is that if you go to momentum space and rotate each momentum mode by k-dependent phase, that group is abelian. These are all phase rotations, whereas our Onsager symmetry is non-abelian. That's right. So that's the reason why it does not belong to that. It's a supporting evidence. So Leon was saying that the transformation of this Onsager, this lattice chiral symmetry takes C to C dagger, and therefore it cannot possibly be part of the infinite symmetry in momentum space. The symmetry in momentum space will commute with the vector symmetry. In fact, I did mention the R chiral global symmetry earlier, although I didn't focus on that one. That R global symmetry is part of that infinite symmetry in momentum space. And that one has no anomaly. Yeah, Max.
Let's say you look at, I don't know, CK.
Yeah.
a state created above the vacuum by
Right,
CPT.
right,
And
right.
you look at the quantum number of that as you change the momentum from 0 to pi.
Let's see if I remember the answer. So for the unquantized, so I talk about two axial charges, right? For the unquantized one, that charge will be a cosine function. So it looks like 1 here and goes to something non-quantized and then come back to -1 at the other end. I think for the quantized one, that state must not have a fixed eigenvalue because the state you mentioned, C dagger K, acting on the vacuum, right? That has a fixed U1V charge. Yeah. I think it does. I think it does.
Can't, right? Because some of the generators of the Onsarga group involve 2C daggers
Yeah.
at different positions. That will
That's a good question. But even if it doesn't, in the continuum, it should go away. I have to think a little bit more about exactly on the lattice. Let me think about that. I don't have the answer on top of my head.
Doesn't it just rotate CK into a linear combination of itself and C dagger of K plus pi? Because the cosine K plus pi is minus cosine K. So adding a
It will,
particle
indeed.
momentum K causes the same energy as removing a particle momentum K plus pi.
Yes. Yeah. It will involve C and C dagger.
But I can ask the same question because you were that again. So let's look at CK dagger, and maybe 15 by pi or whatever it needs to be. So it's a finite set. How does this symmetry act on these finite sets? So the infinite set or the large set CK will break into a very, very large number of finite dimensional representations of this output. Is that right?
Don't remember the. Well, it will definitely mix. It will definitely mix CK with CK dagger and maybe CK plus pi dagger.
But there's a finite set.
Yeah. Yeah, because they both commute with the Hamiltonian, so at every energy eigenlevel, yeah, there's only finitely many of such things. But that's not the contradiction, right? I could have. That could be it. The representation theory of the Onsarga algebra was analyzed, and I think it does have, well, it has to have finite dimensional representations. And the low-lying states have to fall into that representations. Yeah. So there was a paper I mentioned by Paul Fendley, which studied the representation, which discussed the representation quite nicely. Oh yeah, maybe Bowen.
The generality of the CPT map on the lattice. So now you are focusing on 1D, but the idea is more general, right? So it's, on any dimension in field theory, you can have this CPT, and can you write down the lattice version for any dimension?
I don't want to make a too general statement, but I think for simple enough Hilbert spaces and for simple enough Hamiltonians, you can easily identify the lattice operators that goes to CRT in the continuum limit. I have a handful of example, and there was a recent paper by Wu Chen and Nati where they did that in 2 plus 1D in a lot of details.
Then do you think it can be simply defined for P plus IP from your model?
So that's a great question, and I can answer that question in 3 words, work in progress.
Okay, sounds good. Thanks.
might see if it works. Okay, it worked. So does imposing Onsarga and CPT forbid all types of interlayer couplings, or are there some interlayer couplings?
There are still some interlayer couplings. Yeah. Okay. Oh, Brendan.
Sorry, one more question. In the continuum, there's a theorem that I won't be able to state terribly precisely, but roughly it says that if you have two U1 symmetries with a mixed anomaly, there's some free sector. Should I understand your result about Onsager plus CPT as being a kind of lattice version of this? Because you said you sort of only allow for quadratic
I think
terms.
it's different though, because on the I think what you have in mind is probably more precise if you bosonize it, right? There's some kind of compact boson. But if you view it from the fermion picture, you can write down a quartic term that is interacting from the fermion point of view, but still preserve the 2U1. What's funny here is that the quartic term on the lattice will violate our symmetry.
I see. Thanks.
Is your realization of CPT on the lattice canonical? My understanding is your realization of a U1 vector and axial are not canonical. There are many choices. Yeah.
I think on this simple enough, well, first of all, there's an ambiguity that you can combine this with a fermion parity. You can put a minus sign here. But that freedom
That's not
is there on the lattice. It's also there in the continuum. Because in the continuum, you can think about the CRT symmetry as coming from pi rotation or 3-pi rotation. On this simple Hilbert spaces, at least for the tight binding Hamiltonian, you can show that this is the correct CRT that goes to the continuum. But more generally, that's a very interesting question that if you just hand me some anti-unitary operator that also reflects one of the spatial coordinates on the lattice, how do I know if there is a Hamiltonian such that this lattice operator goes to the canonical CRT symmetry in the continuum? I don't know the general answer to that question. In fact, we listed that as one of the open questions in the paper with Nati and Wu Chen. For this simple Hilbert spaces, there aren't that many other options. All right. So I have 7 minutes left. Okay, that should be enough. All right, so in this paper with Wu Chen and Nati, we talk about half of the system we discussed earlier. So now the UV Hamiltonian is just the gapless Kitaev chain, which goes to a single non-chiral Majorana fermion. Has the left mover lambda L and the right mover lambda right. And you can, in the continuum, there's a discrete chiral symmetry. This is half of the system, so we no longer have a continuous chiral symmetry. Instead, you have a discrete chiral symmetry. And that discrete chiral symmetry arises from the lattice translations of one Majorana fermion. The discrete chiral symmetry in the continuum, its order is 8. This is a famous 8, and here are some relevant references. But the Majorana lattice translation, as it turns out, only has an order 2 anomaly. So there's again a mismatch. And the punchline of that paper with Wu Chen and Nati is that if you further impose a lattice CPT, then you get the order 8 anomaly on the lattice, which matches perfectly with the continuum. And these are not the only papers about lattice CPT. I also want to highlight 2 other papers. There was a very nice paper by Ogata from a few years ago. She was studying invertible fermionic phases in 2+1D. And she found that the lattice classification doesn't match with the conjecture classification in terms of the cobordism group, but they match if you are willing to impose a lattice CRT symmetry. There's also a very nice paper by Nikita Sopenko discussing the role of lattice CRT in invertible phases. All right. So let me summarize my talk. So in addition to the vector U1, we found that there's actually an exact lattice axial symmetry, which acts on the fermions in this creative way. However, the lattice vector and axial charges don't commute, and they generate the Onsager algebra. This Onsager algebra forces the Hamiltonian to be gapless. And in that sense, we say that the Onsager algebra on this lattice chiral symmetry has an anomaly. The orders of the lattice and the continuum anomaly only match if we impose a lattice CPT symmetry. One thing I didn't have time to talk about is that there's another lattice axial charge which generates a non-compact R global symmetry. But that non-compact R global symmetry is part of the infinite dimensional symmetry when you go to the momentum space. But that symmetry has no anomaly. The easy way to see that is that on the lattice, you can, since it commutes with the vector charge, you can add the vector charge as a deformation term to the Hamiltonian, which is also known as the chemical potential. And then you just lift the chemical potential to be high enough, and you go to a trivial phase. You might be wondering what the corresponding term is in the continuum. Of course, you can also write down a chemical potential in the continuum. Wouldn't that trivially gap the phase? But that wouldn't, because in the continuum, the sine function, the hill of the sine function becomes sky high, and no amount of chemical potential can ever gap it out. So that's kind of the curious mechanism how an anomaly-free, non-compact R-global symmetry can become an anomalous Schringer, can become the Schringer anomaly in the IR. There are several outlooks. The first one is more like a confession that we made some progress in our discussion of the anomaly. We should also include ancilla. We have made some progress towards that, but not completely. The second one is how to understand how the anomalies can get canceled on the lattice if you have multiple flavors. There was a nice paper by Shu from last year. I also want to highlight two very recent papers, one by Ryan, John Presco, Lucas, and the other last night by Shu-Heng, where they use a different model, the modified Villain model, which has infinite dimensional local Hilbert space, to discuss anomaly cancellation on the lattice. Another natural question is to study 2 + 1D SPTs for our lattice chiral symmetry. And perhaps the most natural question is, what are the higher dimensional generalization? I have 3 minutes left, so I can use one slide to summarize some development over there. So in this talk, there's a UV Onsager algebra, and we talk about how it becomes the chiral symmetry in 1 + 1D, matching the Schringer anomaly. In another paper with Shao, Arco, and also Luke Kim, who is a student at MIT, we found that there's a similar Onsager algebra in some 2 + 1D lattice model on a honeycomb lattice. And that symmetry, that Onsager symmetry, when you further impose time reversal symmetry, will match the parity anomaly in the continuum. There's also a very nice paper by Ryan Thorngren and Lei Joya, where they talk about some 3 + 1D model, where there's also an Onsager type symmetry, and in that case, that matches Witten's SU2 anomaly. So it seems that this kind of non-abelian algebra is capable of matching many different kinds of anomaly in the IR. In Ryan and Lei's paper, they also have a non-compact R global symmetry that goes to the ABJ anomaly in the IR. All right, I have 2 minutes left, and that's the perfect timing to conclude the talk. So in the last slide, I put down some picture of some happy memories with our UQM friends. And with that, I thank you for your attention.